Good evening, everybody. I am about to steal a couple of minutes before the program really begins and you get the chance to hear Professor Bialek. I work with Science Gallery Bengaluru. For those of you who don't know me, I'm the director of the newly established Science Gallery in the city. And we have this week launched our very first exhibition season called Submerge. It's about water, and it's been put together at the Bangalore International Center, and it'll run altogether for 45 days, ending on January 30th. So I urge you all to come and visit us. Just a word about us. We are a Government of Karnataka funded and promoted institution, a part of an international network of galleries, globally in London, Dublin, Melbourne, Venice, Detroit, and Rotterdam. In Bangalore, we have incredible academic partners, Indian Institute of Science, National Center for Biological Sciences, Shrishti, and I myself work very closely with the International Center for Theoretical Sciences, also Senior Associate Fellow there. And so it would be wonderful to see many of you come along. The one thing I can say about our exhibition is that the programming is just as important for us as the exhibits. Our exhibits have been drawn from a pool that was returned to an open call. We received around 130 global submissions, of which 10 are on display. And they're from all over, from Tel Aviv to New York to Tokyo. And for the programming as well, we have fellows coming from all over the world. We have a lecture series, we have a film festival, we have hands-on workshops, and we have master classes, and we have performances. For at least the young here, many of you will know Rahul Ram, who is a toxicologist turned musician of the Indian Ocean. He'll be doing a performance as well. So I trust I've said enough to make the exhibition an attractive proposition for you to show up before January 30, but certainly please do show up for our programs and our lecture series, which is called Confluence. It is in association with the Indian Academy of Sciences and curated by Professor Shrikant Shastri of JNCSR. So as you can probably by now guess, we work with pretty much every single science institution in the city. Please do come along, and thank you to the Planetarium and BASE and to the International Center for Theoretical Sciences for allowing me to steal a couple of minutes at the start of this talk. Over to you. Thank you.
Okay, good afternoon, everybody. And just on behalf of ICTS and the Planetarium, I'd like to welcome you to this talk by Professor William Bialek, who will be introduced in some detail by Vijay Kumar. And thank you for being here in these times of great political entropy in our country. And it's amazing to see that all of you could actually come here for this great talk. So on behalf of ICTS, I welcome you. Look forward to a great talk. Yeah. Vijay.
Okay, thanks, Penta. So it's a great honor to introduce Professor William Bialek. So Bill did his early education in Berkeley, University of California, Berkeley. Did a couple of postdocs in Europe and US, and then he was at the Berkeley again, and then he joined Princeton in the early part of this century. Bill is a theoretical physicist by training, but then he moved to exploring the physics of living systems and has made very deep and fundamental contributions to the way neurons process information, and recently has moved to the area of exploring how organisms develop and how physical principles of information flow, organization really are enabled in organisms placing their organs very, very precisely. It's something where there's a real deep confluence of physics, mathematics, biology, and so on. Bill is a fantastic teacher. He's part of the ICTS, ICTP ongoing, just concluded program on quantitative systems biology, where we had a fantastic set of lectures by him. He's a fantastic teacher. He's been coveted with the President's Award for very excellent teaching. And there's a long list of awards, the most recent being the Max Delbruck Prize for Biological Physics. So with that, I just want to introduce the topic that he's going to say. I won't talk about the topic itself. So this is 150 years of entropy. So the entropy is a very central concept in statistical mechanics. And so this equation that was featured in the poster is actually Boltzmann's entropy equation. The subject is a subtle one, and I just want to introduce by a quote from this book by David Goodstein, States of Matter. There's a chapter called Statistical Mechanics, and he starts off by saying the following. So he says that Ludwig Boltzmann, who spent most of his life studying statistical mechanics, died in 1906 by his own hand. Paul Ehrenfest, Boltzmann's student, Paul Ehrenfest, carrying on the work, died similarly in 1933. Now it's our turn to study statistical mechanics. Perhaps it'll be wise to approach the subject cautiously. So Bill is going to talk about entropy today. Thank you, Bill. So before he takes over, I'm going to request Professor Spantavadia to hand him a memento on behalf of both the Planetarium and the ICTS.
Oh, thank you. I don't know what the etiquette is, but I think I'll save this for later. So it's a great pleasure to be here and to see so many people. Theoretical physicists have a deep belief and a deep appreciation for the fact that we can use the power of mathematics to describe the natural world around us. And indeed, it's not only that we can describe the natural world around us, our description is sufficiently powerful that we can use it to change the world around us. So the foundations of engineering are our understanding of the fundamentals of physics in many cases. So the reason that one can build these things is because we understand what electrons do deep inside the chips that power all of modern technology. And understand is not just a qualitative idea, it's a quantitative one. You know, in the US, science education for children, they often hold up the example of Thomas Edison, the inventor. And I actually think this is one of the worst things we do for children. Because Thomas Edison's approach to invention was trial and error. The idea that you could eventually have an understanding that was sufficiently good that you could predict in advance what would happen when you tried something was completely absent from Edison's method. And while you could invent the light bulb by trial and error, you can't build a smartphone by trial and error, right? You don't just start putting things together and see what happens, right? There's no path that leads us to the technological world that we live in that doesn't rest on having a very fundamental understanding which is powerful enough to make quantitative predictions. So, as physicists, we have this appreciation for the power of mathematics to describe the world. This is, I think, one of the great divides even between the physics community and other scientific communities, where mathematics has been less successful in describing the phenomena. So as Vijay mentioned, I work at the borders between physics and biology, and you know, the phenomena of biology are complex in ways that we all appreciate as humans, but they're also complex in ways that make it difficult to capture them in mathematical terms. And so part of the tension between physics and biology is precisely this difference in the role of mathematics. But when we go from the physics community to the general public, then the gulf becomes very large. And sometimes I think we speak past each other. So as physicists, we approach situations in nature or in the engineered world, and we just believe or act with complete certainty that it should be possible to capture the phenomena in mathematical terms and make quantitative predictions. If you haven't had the education of seeing how this works again and again and again, there's no reason why you would share that belief. And so one of the things that I think is an important challenge for theoretical physicists in trying to speak to the general public is to convey this sense of the power of mathematics to describe the world. That's really central to what we do. It's why, for instance, we believe that it should be possible to write down equations that describe global climate. We know that it's complicated. We know that there are uncertainties, but we believe there should be a description that is accurate enough that we can make predictions and guide policy. Now, you could disagree about the details, but the idea that there exists such a path, if you want, a kind of rational path to policy about global climate, that's something that's deeply rooted in our experience of successfully describing the world in mathematical terms. So, how does one convey our really delight in the fact that mathematics describes the natural world and has power? What I'd like to do is to give, I think the way to do it is to give you examples, right? I can't give you examples in the course of an hour, the substitute for 5 or 6 years of education. But what I'd like to do is to choose an example where the power is evident because of the range of phenomena that it captures. So the idea that we're going to talk about is entropy. And what I'm going to do is take you on a tour of several of the places where entropy as a concept, which is in the end a mathematically precise concept, has arisen in our efforts to describe the world. And it starts in the 1850s with a subject which we call thermodynamics. And essentially, it's if I want to be not to be so grand about it, it's the bookkeeping or the accounting for energy and heat, particularly in practical things like building a steam engine or building a refrigerator. We don't see so many steam engines anymore, but we still have refrigerators. So let's say here, we start by trying to think about refrigerators and heat flow. 30 years later, 20, 30 years later, in the 1870s and 80s, people started to take more seriously the idea that matter was made out of atoms and molecules, out of discrete things. Now, of course, this is an idea that goes back millennia, but you may or may not know it had actually fallen out of favor. That by the mid-1800s, most people did not particularly think that matter was made out of atoms or molecules, and they thought that it was just some continuous flowing stuff. And it was a very controversial idea. This is one of the reasons, well, it certainly contributed to Boltzmann's depression, which led to him taking his own life. But the real innovation, in many ways, from a mathematical point of view, so the idea that the world's built out of atoms, that simply was not a new idea. It was a 2,000-year-old idea. But what Boltzmann and others in the 1870s did was they realized that there must be so many atoms that keeping track of every one of them would be a fool's errand. That if I want to describe what's going on in this room, why is it that if you open one more window, the air flows, the air, you feel the breeze coming in, or not, so on. If I want to understand why there's pressure on the walls that comes from the air, or pressure on us from the air that's above us, I shouldn't try, even though I know, or at that point believed, that the air was made out of lots of molecules, I shouldn't try to understand this by thinking about what every single molecule was doing. I should imagine that what's happening, one way to think about it is that the processes of that many molecules interacting with each other become so complicated that they effectively become random. And so you should think not about the rules by which molecules move around, but rather the probability that something that you might find a molecule in a particular place or moving at a particular speed. And so in the 1870s, there emerged this subject called statistical mechanics, which is essentially the merger of two ideas. One is the atomic hypothesis that matter is made out of atoms, plus a set of notions about randomness or probability, that was somehow the right language. And the remarkable thing was that these different views connected to each other, as I'll explain. But I want to be sure you know how far we're going to try and get before I dig into the individual pieces. So the next steps take a little while. And it's not until the 1940s that two things happen. One is that people get the idea that our everyday interactions with one another, where we ask questions and hear answers and tell each other things that we know or learn about things that we don't know, that behind that, right, we say when we do this that we're exchanging information. And in the 1940s, people started to focus on the idea that maybe this notion of exchanging information was something that could be made mathematically precise. Which is a very beautiful idea, because often when we think about the use of mathematics to describe the world, we tell the story of the astronomer Tycho Brahe measuring the motions of all the planets, and then Kepler understanding that you could make sense out of all of this data by realizing that the orbits were ellipses, right? But here, so mathematics entered our description there by looking at real data and trying to draw, if you want, find an equation that predicts the way the data will look. So what happened in the 1940s was completely different. We took an everyday phenomenon, the exchange of information, and people tried to attach mathematical language to that everyday phenomenon. It wasn't like anybody had made a quantitative measurement of people exchanging information. In fact, it wasn't clear how to do that because it wasn't clear how to attach a number to how much information you gained when you heard the answer to something. And that was the problem that they solved. So what happened in the 1940s is that our qualitative notion of information was made mathematically precise. In the same body of work, so also in the 1940s, people asked a different question. Not when I ask you something, how much information do I gain when I hear the answer? But rather, if I wanted to write down the answer, how much space would I need? And so in the context of my asking you one question, that doesn't sound like a very interesting thing to know. I mean, how much space does it take to write down the answer to a question? I don't know. I usually have a piece of paper big enough to write down the answer, so I don't care. But if you go home tonight and decide that you want to watch a movie on your computer, or for those of you who are watching this being live streamed, okay, the question that you're asking 30 times a second is, what is the image in front of you? And that image is really quite large. It has millions of pixels in it. And so 30 times a second, you get an answer to this very complicated question of what's happening in every one of those million pixels. And the question of how much space it takes to write down that answer is the question of how much you're going to pay to your internet service provider for having that arrive in your home. Okay? Because it has to be written down somewhere, and the physical material is what you're paying for. Okay? So the question of how much space it takes to write down the answer, or how much space it takes to write down information, would become central to our interactions in the world today. It's the understanding this is, in particular, understanding that it is possible to represent information in much less space than you might have thought, but there really is a minimum amount that you need, is central to modern electronic communication. So this problem of the space to write data or images or information, another problem. So the remarkable thing, which is what I'm going to try and explain to you, is that entropy is the answer to all of these problems. And it is the same mathematical object in every single case. And that means that in some strange way, the problem of how much space it takes to write down things on your hard disk, on the hard disk of your computer, is related to questions about how much power it takes to run your refrigerator, which seems very strange. Okay? And the reason that I'm choosing this is precisely because that is so strange. And I hope that you'll get a sense for the way in which mathematical concepts then can bridge these enormous distances. There's one more, actually. In the 1970s, it was realized that these exotic objects which appear in Einstein's theory of general relativity, black holes, which, if you're a community of people who's paying attention to science developments, you realize this has become, again, a central subject. That these rather exotic seeming objects obey a set of rules which look very much like the rules of thermodynamics that this whole subject began with. And so, again, the concept of entropy appeared in a place which is literally light years away from where it started. So, I want to take you on a little bit of a tour of this. I'm told that sometimes people actually have the courage to interrupt and ask questions. And so you shouldn't be shy. As I told the students at the course at ICTS, if I say less but you understand more, that's okay. So if something is confusing, probably you're not the only one in the room who's confused. Stop me, okay? So that's the plan, and we'll see how far we get. So let's talk about thermodynamics. So let us cast our mind back to the 1850s. So in some sense, in order to understand the origin of ideas about entropy and thermodynamics, you have to understand one more idea, and that's the idea of energy. So that's one that is probably more familiar. And one of the things that we learned about energy from Newton and the great period of understanding, the motion of the planets around the sun and everything else, is that energy is conserved. So if you want to predict the orbits of the planets around the sun, one of the things that you can start with is that the energy of the planet as it moves will stay constant. And the energy has two parts. There's the part which is from the fact that the planet is moving, it's called kinetic energy, and the part that comes from the force of gravity that the sun is tugging on the planets with. Okay? So there's a component of the energy which is called potential energy that comes from gravity in that case, and there's a component that comes from the motion. And together, they stay constant. Okay? When you watch, so for example, if you sit on an old-fashioned car which has real springs, right, and you jump off, the car kind of does this, right? So what's happening is that as the spring is compressed, you store energy in the spring, and then it comes back out with the motion of the car, right? So the car, right? And it's actually pretty interesting that even a rather light person can sit on the car, and if you jump off quickly, the car will actually move a little bit, despite the fact that the car weighs, a ton. So, and it all works out, right? You could, in fact, the amount by which it moves is something you can calculate. Okay, wonderful. There's only one problem, and that is, in our everyday life, it does not seem like energy is conserved. So, for example, if I take a rock and I carry it up the hill, then, so here's the hill, here's the rock. You bring it up to the top of the hill. Well, we would say in colloquial English that you were doing work, right, as you carried it up. And in fact, that's the term we use in physics too. You were doing work. And so far, there's no problem because you did work and the energy of the rock also got higher. This is the potential energy from gravity, right? There's a force pulling the rock down to the center, toward the center of the Earth, and you're now 100 meters further away from the center of the Earth. So the energy is a bit higher. And indeed, if you let the rock slowly fall back down, you can get the energy back out again and do something useful. Okay? Like lift another rock, that's the easy one, but maybe you could do something even more interesting. You could turn a wheel and grind wheat or something, right? Right? You know that, right, by the waterfalls, right? You put a paddle in the waterfall and the water is falling down, so its energy is going down, and that gets converted into the rotation of the wheel, right? It's all fine, except for one thing. Suppose you very carefully carry the rock up to the top of the hill, and you leave it there. The energy that you put into the system is stored in the fact that the rock is at the top of the hill, in the same way that there's energy stored in the spring when you compress it. But now, your nemesis comes along and kicks the rock. And unfortunately, the hill is a real hill, not an idealized hill. So it actually is rough. And there's little plants growing, right? And there's stuff in the way. And there's a valley, and in the valley maybe there's even some water. Okay, you can keep going. And your friend kicks this thing, and what happens? It just falls to the bottom. And right here, you might say, okay, what's happened is that all the energy I stored has been turned into the kinetic energy of the rock, because it's moving. Except you all know what happens. It goes to the bottom of the hill, and it stops. So where did the energy go? I had stored energy in the system by bringing the rock up to the top of the hill. I seem to have converted that potential energy into kinetic energy by giving it a push, but then somehow it all went away. It's back at the bottom of the hill, so it doesn't have the potential energy, and it's stopped, so it doesn't have any kinetic energy. So where did it go? There's a notion of friction. But the conservation of energy in mechanics doesn't have any exceptions. So so people started to appreciate that there was this problem that in the real world, and the world of our everyday experience, the things that we watch, like the rock, don't move quite according to the laws that govern a planet going around the sun. There are extra terms in the equations, and if you just focus on those terms, they violate the conservation of energy. But this is very disturbing, because if I can violate the conservation of energy, in this example, I lose energy. But if I can violate the conservation of energy, who's to say that I can't make it appear spontaneously? Which, this one's just frustrating. But if energy starts appearing in different places spontaneously, that could actually be dangerous, right? So maybe you'd like to know for sure that this isn't going to happen. So how can I reconcile my everyday experience with the conservation of energy? And so what people realized is that, roughly speaking, what we called energy had two parts. There's the part that we can see and use, like the work we do when we carry the rock up the hill, or the work, the useful things we could do by carefully letting the rock fall back down in some controlled way. But then there's an extra part, which is called heat. And indeed, if you check carefully, you'll notice that whenever there's friction, things get warmer. So this is also heat in the everyday sense of the word, right? So, and furthermore, heat can flow. And it can flow from a small region into a large region. So for instance, if you have a big bucket of water and you shine a bright light that makes only a very narrow beam, then you know that you heat up the water underneath the light. But if you sit there for a while and you put your hand in the water far away from the light, you'll notice that it's also warmer. So the heat that was being put into the water by absorbing the energy from the light can spread. And if it's a really big bucket, it spreads out so much that you essentially can't find it anymore. And so that's what happened to the energy of the rock. It bumped against another rock, and as it bumps, it leaves behind, it rubs a little bit, and just at the surface where they rub, things get a little bit warm, but then that extra heat flows throughout the entire rock, the entire small rock, and then it brushes against a plant, and the same thing happens, and so on. And at each step, from the point of view of the rock, you're losing a little bit of energy. But that energy doesn't disappear, it just goes in places where you can't find it. So there was this great discovery that you could keep track, in some sense, of the energy that is hard to find. Okay? And that's heat. And that really is the same thing as the heat that you use in order to warm things up. Okay, so that's energy. And in this way, the conservation of energy was saved. Now, if I take this water, which I'll do something useful with, I can ask, what is the energy of the water in this bottle? That actually turns out to have a meaning. So not only, I lifted it up so it has a little gravitational energy, but also the energy, the molecules inside the water are moving around, and so they have an energy and so on. So I can ask, what is the energy content of the water? It turns out, so then you say, okay, that's good. But I've learned that in order to make conservation of energy work, I have to have these two kinds of energy. There's the sort of the one that's easy to keep track of and the one that's hard to keep track of. So can I ask you, what is the heat content of this water? And it turns out that, try as you might, I can talk about heat flowing into the water, right? And I can talk about heat flowing out of the water as it cools off. But I can't make sense out of the idea that the bottle of water has heat content. Because in some sense, I can't tell whether this is a bottle of water that somebody took out of a freezer and let it warm up, or it was something that he took from outside and put it in the refrigerator and made it cool down. Right? And there's no way to keep track of all that. And as you have some poor fellow who's carrying the water around, right, and putting it in different places, keeping track of the heat that goes in and goes out, it doesn't work. There's no way to talk about the heat content. And so what people figured out in the 1850s was that if you talk about the heat flow and divide by the temperature, and you have to be careful to measure the temperature in the right units, then this is a change in something which they called entropy. And if you check the heat that at every step of a process, if you check the heat that flows and the temperature at which it happened, and you add up this quantity, then you get something that you can talk about as a property of the state of the system. So I can talk about, I can't tell how much heat, I can't add up the heat that goes in and out of the bottle of water. But if every time the heat flows, I also check what temperature the water was and divide, then I can add that up, and no matter what process brought the water to this table under these conditions, the answer will be the same. So in this sense, entropy was first introduced as a bookkeeping device, right? It allows you to keep track of the flow of heat in and out of systems in a way that you can say, I know where I am now. I don't need to know everything about the process that brought me here. But then they discovered something else, which is that the entropy always increases. And this, yes? Okay. So the idea is that, let me take one step. Let's say when I'm taking the bottle of water out of the refrigerator, okay? And I let it warm up. And at each moment, since it's warming up, you know, there's some heat that's flowing into the water. And at that moment, it has a particular temperature. So if you try to add up how much heat, let's do it minute by minute to keep it simple, right? So every minute, a certain amount of heat flows into the water. Okay? And then suppose you tried adding up all the heat that flows into the water every minute, and after a while it's going to stop, right? Because the water comes to the temperature of the room. Then let me do something else. Let me take the water, and I had put it into a pan on the stove, and I had heated up. And now I take it off the stove and bring it to the room. Now heat flows out of the water into the room, right, because it was warm. And you could try adding up the heat that flows at every moment. But now you can imagine going around in a cycle. You heat it up, you warm it up, you cool it down, and if you do that, then as you add up the heat around the cycle, it doesn't cancel out, right? It should cancel out, because if I start in the same place, and I put it in the refrigerator, I put it on the stove, and then I come back to the same place, it's accounting, right? Nothing's supposed to happen. If I end up in the same place, I end up in the same place. But it doesn't work. But if at every step you divide by the temperature, and you say that there was a change not in the heat, but in this abstract quantity called entropy, then it works. Okay? And so you can talk about the entropy of the water in this bottle, but you can't talk about the heat content. That was the surprise. And that's the first place their entropy arises. And then everybody realized something that is incredibly profound. And in fact, I already used this idea. When I told you when I said, when I take the bottle of water out of the refrigerator, heat flows into it to warm it up. Why does heat flow into it to warm it up? So, right, if I take something out of out of the freezer, then it does not happen that the heat flows out and it gets colder. It's the other way, right? What's the principle behind that? So it turns out you're mixing two ideas, but they're both correct. So let me pull them apart a little bit, and I hope you'll see. We should check in a couple minutes whether, okay. So what people realized was that in any process that happens in the world, there's one thing you can be sure of, and that is that the entropy of the world will have increased. And what that means is, in particular, so that's called the second law of thermodynamics. Yes? It's the temperature. Let's think of it as the temperature of the thing you're watching, right? And you watch the heat flow. I'll use this in just a second, so maybe it'll become clearer. So suppose I have two objects. The bottle of water I just took out of the freezer and all of the air in the room. So since I'm not doing any work, energy and heat are the same thing. So since energy is conserved, if heat flows into the water, it better flow out of the air. And it better be the same amount. But what you notice is that what matters for the entropy is how much heat is flowing divided by the temperature. So if I'm at a very low temperature and heat flows into me, my entropy goes up by a lot. But if you're at a high temperature and heat flows out of you, your entropy goes down, but only by a little bit. And so the real principle here is not that heat flows, or the observation that we've all seen, that heat always flows from the hot object to the cold object, is really the principle that the entropy of the world is always increasing. And this principle you can use in much more general situations. Okay? And it was the generality of that that made it be called a law of thermodynamics. Right? And this is why, for example, you can't build a perpetual motion machine. So the energy is conserved, and the entropy of the world is always increasing. So remember that the reason that we have that energy conservation doesn't look quite right in the everyday world is because there's heat. But then this is telling you that that heat has to flow in a way that the entropy of the world keeps going up. And this tells you that you're always going to have to pay, right? Because essentially, if you succeeded in getting the energy that you want in some place, then since the entropy of the world wants to go up, if there's any way for the heat to flow, to let the entropy of the world go up, it will. And the energy that you concentrated in one useful place will be dissipated. Yes? Sorry? So I think the closest to frictional energy is the heat itself. And so then this is a way of keeping track of those heat flows. So that was the 1850s. So we're 150 years back. Let's try to jump to the 1870s. Jump 20 years ahead. Still 100 years ago, but 20 years ahead. So let me do this in the sort of quickest and simplest way possible, I think. I imagine that the material that I look at, like the gas in this room, or the water in that bottle, is made out of atoms or molecules. And these molecules are moving around. And when I look at this bottle of water, I don't have the slightest idea what all of those molecules are doing. I do know that the water takes up a certain volume. I know that it's at a certain temperature. Right? I know that it has probably some minerals dissolved in it. I know some facts, but these are very macroscopic facts. They don't tell me the details of what all the molecules are doing. And so there's a very simple to state idea, which has an enormous amount underneath it. And that idea is, can you count the number of ways to arrange the atoms consistent with your macro observations? So in particular, right, if all the molecules were twice as close together, then the water wouldn't take up all this space. So I know that the molecules have to be distributed over this whole range. For example, okay? And you could give more examples. There's a little less now. And so what people, particularly Boltzmann, but Maxwell, Gibbs, many others, set out to do was to say, can I count, if I have a model for how the molecules are moving around and how they interact with each other, can I count the number of ways I can arrange them, where I can put them in space, what velocity I can give to each one of them that would be consistent with what I see on the scale of a meter, on the scale that I can hold in my hand. And this is like, for instance, an exercise which many of you might have done in school, which is to say, suppose I flip a coin 100 times, you know that most of the time you'll get around 50 heads and 50 tails. And the way you show that that's the most likely thing is, right, for the individual coin flip, it doesn't matter. It could come up heads or it could come up tails. But in order to get 100 heads, then every single time you flip the coin, you have to have heads. But to get 50 heads, there's lots of different ways of doing it. You could have 50 heads in a row and then 50 tails in a row. Actually, that's not very likely. But you could also have head, tail, head, tail, head, tail, head, tail, right? And there's lots of different ways of rearranging things so that you still come up with 50 heads. So that's the idea. 50 heads is a kind of macroscopic observation, right? You sort of sweep together all the coins and take a look. And then the exact arrangement of the coins is like what all the atoms are doing, or all the molecules are doing inside the water. So you count. And just like with flipping a coin, the hypothesis is that the different ways of doing things are all more or less equivalent to each other. And what's really important is how many of them there are. So if that's true, then the things that you see in nature should be the things that have the most number of ways of happening, right? Those are the most likely. So if you call this number W, so in English we would say it's for the number of ways of arranging things, but actually it arises in German. What Boltzmann did was to understand how to compute this number. And then he said that you should take its logarithm, right? So logarithms, right? The logarithm of 1 is 0. The logarithm of 10 is 1. The logarithm of 100 is 2. So you're counting by how many times you have to multiply, right? The amazing thing There's many things going on here, but to get to the heart of the point I want to make, if you compute this quantity, the number of ways of arranging things, arranging all the molecules, and you take its logarithm, then except for a constant, which has to do with what units you choose, so actually I'm going to erase it because units are arbitrary, then this quantity is in fact the entropy. And what does it mean when I say it's the entropy? Well, first of all, I could just define this to be the entropy, but why does it turn out to be the same as this entropy? That's the amazing thing. So by counting the number of ways of arranging all the molecules inside the water, I learned the entropy of the water, and it's the same entropy that appeared when I thought about heat flows. And what that means is the reason that the entropy of the world goes up is because the world is always looking for conditions that give it more ways of doing things. And so the second law of thermodynamics, I'll get to you in just a second, the second law of thermodynamics, that the entropy of the world is always increasing, is really the statement that the constraints on systems, the macroscopic behavior of systems, will always move in a direction that gives the molecules and atoms that you don't see more ways of doing things. Gives them more freedom to explore. There are a couple of questions. One and one. Yes? No. No. One bridge too far. We can come back afterwards. You had something in there. Yes. So indeed, in classical physics, if I put all the atoms into a perfect crystal and I don't let them vibrate, then the number of ways of arranging things is 1, and so its logarithm will be 0, and you're right, the entropy will be 0. Yes? Yeah, 1 and 1. So you can be in a state where everybody's jiggling around, but for example, the whole thing's in a box, and you've insulated it with a thermos so the temperature is fixed, and the entropy will not go up. The fact that they're moving around is associated with their entropy. Yes, if you stopped the motion, the entropy would go down. But it doesn't, there's a difference between what the entropy is and whether it's increasing. No, you're being, so, I mean, yes and no, okay? So, the fact that the atmosphere ends up getting warmer as the result of the external constraints is the second law doing its thing. But the whole system is being driven by the sun, right? And the extra warming is a result of greater constraints that are put on the energy exchange between the atmosphere and the rest of the universe by the stuff that we've put up there. This is great. Of course, I've only gotten through half of what I want to say, so let's do a couple and then I'll see if I can go quickly through the second half. Yes? Yes, so the statement that the entropy of the world is increasing is a kind of global statement, and one has to be a little bit more precise. Eventually, right, given a certain set of constraints, there's a maximum for the entropy. And at that point, you've come to equilibrium. So in particular, when the temperature of the water is the same temperature as the room, no more heat flows, and there's no more entropy increase. Now, when I open the window, the temperature of the room changes, and heat can flow again. But if I imagine that the temperature of the room is fixed, then the heat flow will stop, and at that point, the water is in equilibrium with the room. So, great question. I think if one wants to stay in this language without building a lot more apparatus, right? When I have a balloon and I open the balloon and the air rushes out, in some sense, the air is expanding into a more available space. Okay, that's entropy. When a bomb goes off, the stuff is carried out further. That was actually energy, not entropy. The expansion of the universe is, right, it's called the Big Bang for a reason. It's more like the explosion of the bomb. It's energy driven. The problem is that saying what you mean by energy in general relativity is subtle. Which is why, but roughly speaking, the expansion of the universe is an energetic and not an entropic effect. On the other hand, the question of what's happening to the entropy of all the stuff in the universe, that's an interesting question. In particular, you might be worried about the fact that as the universe is expanding, structure in the universe is being formed. So in fact, the particles in the universe are becoming more organized with time, which seems like their entropy is going down. So there is a problem. We know that you can make the entropy of things go down, right? I take something and I cool it off. Eventually it becomes a crystal, and I've sucked all the entropy out. So it's okay. I mean, I paid for it somehow, right? By plugging my refrigerator into the wall, my freezer into the wall. Yes, this is the question of whether the world will end with a bang or a whimper, right? So let me see if I can get back to the theme. So what I hope you got out of this is that in the 1800s, we have these two very different ideas about entropy. One is about counting what all the molecules are doing, and the other is a kind of accounting of heat flows. But it turns out they're the same. Which, by the way, is a little surprising at many levels. And so I'm torn between trying to help you understand and also trying to plant the seeds of things for you to worry about and think about later. The seed that you should, to help you think about things later, let me emphasize how bizarre this is. Because remember, the thing that you're counting is the number of ways that you could arrange the molecules. They are, at this moment, only arranged in one way. So why is it that the possibility of more arrangements somehow has a physical meaning? In fact, it has a very direct physical meaning. And it's, by the way, it's an everyday phenomenon. If you take a balloon and you push on it, you feel a force. If you go very carefully through the whole analysis, you will discover that the energy of the molecules inside the balloon is not changing. But if you change the volume that is available to them, then the number of ways of arranging them goes down. You're changing their entropy. And the force that you're feeling is really a force that results from the entropy of the gas, not the energy of the gas. So this business of counting the number of ways of arranging things turns out to have this very direct physical consequence. So that's the discovery of the 1800s. Let me take a few minutes and jump ahead to what happens in the 1940s, and I'll go a little more quickly. So the history of this subject in the 1940s is both complicated and simple. So it's complicated in the sense that there's a number of people who do things that are sort of precursors to the key ideas, as is often the case in science. Once you have a complete change in your understanding, you can look back and find people who had pieces of it, but they never quite put it together. But then the amazing thing is that in one paper, one guy puts everything together, And he creates the foundations of a subject which still is vital, as I explained, to all of modern information technology. So the guy was Claude Shannon. And these papers came out in 1948. And in this paper, he did many, it's a very long paper, and there's also this interesting fact that if today, as a student, you want to learn this subject, it's actually easier to read Shannon than to read a modern textbook. Because Shannon used incredibly elementary arguments. In fact, I would say that a student who has a good preparation in high school mathematics should be able to read Shannon's original paper. And it's an extraordinary thing to read. So he did many things, and I just want to focus on two things. One is, he said, imagine that you ask a question, and then you hear the answer. And the answers, well, as a result of hearing the answer, you gained information. And so what he asked was, is there a way of attaching a number to how much information you gained? And in order to make this problem well posed, what he said is that I will imagine that before you hear the answer, you do realize that there's a set of possibilities. So the answers could be labeled 1, 2, 3, so on, up to some number n. And in fact, not only can you imagine the possible answers, you know that some of them are more likely than others. So if you'll forgive me a little bit of formalism, you could say that answer number 1 has probability P1, answer number 2 has probability P2, answer number 3 has probability P3, and so on. So, what is the temperature going to be at noon tomorrow in integer number of degrees? So there's a set of answers, right? From 0, which I presume is not very likely, to, 30, 35, something, right? So you have one, that's the answer. And you could ask this question today, you could ask it tomorrow, you could ask it tomorrow. And so because it's December and we're in Bangalore, some answers are more likely than others. And if we're careful, we can go to Google and we can find that little picture of what the distribution is like, right? But the actual temperature tomorrow will be something. And if I knew what that was, I could use that information to do something, right? To figure out what I should wear or I don't know, what to set my air conditioning to. I don't know, okay? I think here the range is actually small enough that I'm not exactly sure what you do with the answer. But where I live, knowing the answer to this question is incredibly useful. Do I need a coat, right? Here I think all possible answers of the property, you don't need a coat. But, okay. So what he said is, can I attach a number to how much information I gained? And actually, let me do the simple case. And the simple case is, suppose all the answers were equally likely. Just to keep it simple, right? And he said, well, wait a second. I know some things, right? If all the answers are equally likely, then if there are more possibilities, then when I hear the actual answer, that gains more information, right? So if I ask you a question and I already know there's only 2 possible answers, I'm not going to learn that much when you tell me which one it is. But if there were 100 possible answers and you told me, I would learn more. And then the other thing is, if my question really has 2 independent parts, then I should be able to think of it as that you answer the first part and I get a certain amount of information, and you answer the second part and I get a certain amount of information. And if they're really independent of each other, I should be able to add those up. Okay? And in this simple context where everything's equally likely, that's actually enough to tell you the answer to Shannon's problem. In the general case, you need one more condition, which is a little complicated, so I'm going to leave it. He said, can I write down a mathematical function that tells me how much information I gain on average when I hear the answer to the question? And I told you there are these conditions you should obey. And the answer is that the only way to obey those conditions is to say that the information is the log of the number of possible answers. So there's only one function that works. And again, there's the possibility of putting a constant in front because nobody told you what units to use, but I'll set the constant equal to 1. You'll notice that this is the same function that appeared over here. So suppose the question that I asked you was, exactly how are all the molecules in this room arranged at the moment? Well, the number of possible answers is the number of ways of arranging all the molecules. And the logarithm of that number is the entropy. Yes? So the two conditions I gave you about it has to grow with n, and if you have independent parts to the question, information has to add, that's what determines that it has to be a logarithm. So there's a technical argument. As I say, it's an argument that makes use of high school mathematics. Okay? So, but time. So, and maybe it's not appropriate. But so what's amazing is that if you try to make our intuitive notion of exchanging information precise, you end up with the same object that appeared when you tried to think about the way molecules behave in matter. That's really extraordinary. Now, in this example, you might say, well, I don't know, there's a log. Okay, well, I don't know, not so complicated. Of course, usually the different ways of arranging the molecules don't all have equal probability. Some of them are a little bit more likely than others, and so you have to do something more complicated than this. And similarly here, in the real world, the different possible answers have different probabilities, and so you have to do something more complicated. What's amazing is that even when you do those more complicated cases, you get the same answer. Okay? That takes more work. So one more. This was very simple. Let's do one more. And this is actually also in Shannon's original paper. And he said, how much space to write down the answer? So let's imagine we're in this same setting. I ask you a question, you tell me the answer, I want to write it down. And I want to write it down, so I should be careful. I should say the minimal amount of space. It's possible that different answers take different amounts of space to write down. In fact, that's almost surely true. So I should say on average, in order for the question to make sense. And then you realize that in order to write down the answer, you have to agree on an alphabet. You know, what symbols are you going to use to write things down? Sorry, it doesn't even need to be an alphabet, right? As you guys well know, there are ways of writing things down that are not using an alphabet. But you have to agree on symbols. And if you agree on all these things, then there ought to be a way of saying what's the minimum amount of space that I need on average. Okay? Now you'll notice, by the way, that when I crossed out this constant, I didn't actually resolve all the ambiguities in this formula. Because, as many of you know, there are different kinds of logarithms. So I can take a logarithm to the base 10, but I could also take a logarithm to the base 2. Or I could take the natural logarithm. So I'm hoping these things mean things to people, right? So in the same way that when you take logarithm to the base 10, you're counting 1, 10, 100, so on, right? So 1 is 0, 10 is 1, 100, the logarithm is 2, and so on. When you take logarithm to the base 2, it's 1, 2, 4, 8, 16, so on. You keep multiplying factors of 2. So the choice of the base of your logarithm is like your choice of numerical symbols. right? We've agreed to use 0 to 9, so there are 10 of them. You know that there's a way of doing it in which there are 16, which is actually quite ancient, but then got used in computers for a while. And of course, there's the possibility of only using 2 symbols. So you only write 0s and 1s. And you can always convert everything into 0s and 1s and convert it back, and that's what happens in your computer. So suppose that we, on this side, agreed that our symbols were 0s and 1s. And on this side, we agree that our logarithms are to the base 2. Then the answer, then the answer to this question, which seems like an incredibly hard problem, right? I have to imagine all possible ways, all the different ways I could encode the answer to my question and search over all of them. But somehow Shannon found his way through this and was able to prove that the shortest code, on average, has a code length, L. So what do I mean by code length? How many symbols do you need? And again, it's on average over all, it's the minimum amount on average. The answer is the same as it was over here. In fact, in the case where they're all equally likely, this is actually quite easy to prove. It's the case where they're not all equally likely, which is the interesting one, because that's the real world, right? If I want to encode an image, not all images are equally likely. For example, if I scramble all the pixels, that actually never happens. So I can easily generate images which in fact will never happen in the real world, which tells you that not all images are equally likely. So the challenge is to do this in the more general case. So that's what Shannon succeeded in doing. And so what he showed is that not only does this quantity, which is the same as the entropy, not only does it make precise our intuition about exchanging information with each other, it also answers the practical question of how much space we need to write down that information. And it says that there is a way of packaging the information so that you have it take up as little space as possible. And then on average, the amount of space that you will need is exactly the entropy of the distribution out of which these things were being drawn. And what's amazing then is that if you take this span, well, it was 100 years of work, but we're now looking back at 150 years. Okay, so just to be clear, right? The fact that there is a way of encoding information which is the shortest possible is the origin of a noticeable part of the information technology industry, right? Which is data compression. So the fact that you can watch a movie at home is because there are ways of encoding the images that push down toward this limit. Okay? And in some sense, what Shannon did was to set goalposts. He said, there is a shortest code. So for whatever problem you're working on, you should try and find the shortest code. It took generations to find codes that actually reach the Shannon bound. Okay? So it was not easy, which makes it even more amazing that he was able to prove the theorem. So let's not go there. I told you there were many things in Shannon's paper. Okay. There's another problem, which is when you're transmitting information and there's a possibility of errors creeping in along the way. That's about channel capacity. This is just about source coding, to say the technical words. So this result, as I say, is the foundation for this whole effort. So you all certainly know that there are files on your computer whose suffix is JPEG or MPEG or MP4, right? You may not know what those stand for. What they are references to the code which is being used to compress the data. Okay? So the fact that you can store all those images on your computer is because they're being efficiently compressed. Okay? And The limit to that compression is what Shannon calculated. And as I say, you should, in one sense, there's a sort of negative statement. You could never compress past it. But in the positive sense, it set a goal for people to find codes that were that good. And that drove the development of that whole field and made possible all the things that we do every day. Okay, so we started with heat flow and refrigerators and taking the bottle out of the freezer and pouring the water into the pan on top of the stove and moving around, right? And the rock rolling down the hill. And lo, these many years later, we end up in the world of information technology. And what I'm telling you is that it's the same mathematical object that carries us all the way through. So what does that mean? It means that if you could measure the positions and velocities of all the gas molecules in this room, don't do the whole room, do a small region. Already you can't do it, so it's okay, right? Imagine that you did that, and then you typed the answers into a file on your computer. And then you ran a program on your computer that compresses the file. So depending on what kind of computer you use, this might be called gzip, it might be called compress. There are other ones, right? But you know, before you send big files to people, right? If you want to mail a big file to your friend, you compress it. Some of that's actually happening automatically on consumer computers, right? So you don't even realize it, like in your camera with JPEG, but as opposed to RAW, right? So some of you who are more serious about photography, you know that there's RAW. That's what you don't compress. Okay? And you'll notice those files are a lot bigger. Okay? So run one of those compression programs on this file where you typed in the positions and velocities of all the gas molecules in the room. And now you'll notice the file takes up a certain amount of space. So depending on exactly how big a region you did, I don't know, it's a few megabytes or something. Now you should warm up the room by 10 degrees and do the exercise again. Measure the positions and velocities of all the molecules, type them into a file, run your compression program, look at the file you get. You will discover that the file is longer. But remember, Shannon taught us that the length of the file, assuming that the compression program does what Shannon said it should do, that is to say, they reach the goal set by Shannon, then the length of the file will be this information content. But this information content is the entropy. But this was an entropy of the answers to a question. But in this case, the question was, where are all the molecules? So it's the entropy of the gas. But remember that the entropy is the heat flow divided by the temperature. So if I measure how much longer the file got, I can go backwards through history and undo all these steps and determine how much heat you had to put into the gas in order to warm it up. And so that means that because of the power of this mathematical idea, which reaches across this century or more, the length of a file on your computer can be related to this which is after all a kind of abstract thing, right? And you might think it would be different depending on, buy another computer, the file length will be different. Yes, it will be. The difference in the two file lengths will not be different, assuming the compression is working. That seemingly abstract thing, which is the difference in the file sizes on your computer, is directly related to the amount of heat that you had to put into the gas in order to warm it up. And for me, that's always been one of the most startling examples of the power of mathematics to describe the world. It is two things that we do every day, right? We go to the stove and we warm things up and we sit at our computers. And it turns out those are related to each other. So thank you for your attention.
To one of the mics, it'll be great if you can go there. If not, I'll.
Good. It was a very excellent talk. The last statement which you made, that is code length, which is giving the information. And this information, which is an ordered thing, equals the entropy, which is the measure of disorder. So order and disorder,
Yes.
that equivalence. So this abstraction which you are talking about, what is actually the reality? I mean, in terms of, like, for example, I want to compress, to the Shannon's limit. I mean, of course, it's very idealistic. I just take a closed system wherein I actually use that energy, the actual heat flow to get that compression. So will that be same? I mean, what is the, instead of abstraction, where is the reality of order and disorder?
So there's a subtlety here which you've put your finger on. And that is that in the context of thermodynamics and in the context of statistical mechanics, so the 1800s subjects, entropy is indeed a measure of disorder. Because in some sense, if I have a state in which, so first let's do the thermodynamic version. As the entropy of the world is going up, heat is flowing in different places. And your intuition, which is correct, is that it's going to sort of find its way into as many places as possible, right? And so in some way, you started in a state where all the energy was in one place and it kind of leaks out. Okay, this is very vague, but captures the sense that things are becoming more disordered. When I go to Boltzmann and statistical mechanics, entropy is literally counting the number of ways that the molecules can be arranged. And as the entropy goes up, the system is moving toward states that have more freedom to move around. And in that sense are, well, what is literally true is they're less constrained. I mean, at any one moment, saying whether you're ordered or disordered is complicated, right? I mean, things are arranged the way they are arranged at this moment. But if I watched for a long time, I would see the system try out many different configurations. And there are many more that are available to it. And so the increase of entropy really is an increase of disorder because the system has more freedom to explore. When I think about information, you have to be very careful. The information that you gain in hearing the answer to a question is related to the disorder of your state when you ask the question, right? So when I ask the question, I know there's 100 possibilities. So in some sense, my mind is dancing among the 100 possibilities, at least implicitly. And if it were 1,000 possibilities, it would be even more disordered. And then when I hear the answer, I would gain more information. So there's a question of whether you should think of information and entropy as being the same or as one being the negative of the other. The way I've set it up, they come out being the same. And that's good because you don't want your code lengths to be negative, right? So it makes more sense to say it this way.
So then, what is loss of information? What does that become? Does increase in entropy cause loss in information by any chance?
So, you'll notice that in this, okay, in the interests of trying to say something rather than nothing, I cut out little pieces and tried to fit them together in a way that leaves lots of things dangling. This situation where you ask a question and you hear the answer, I don't know about you, but I think that's a very rare situation. Usually you ask a question and you can imagine many possibilities. And when the person tells you something, you don't really know the answer. You know that certain things now aren't possible and other things have become much more likely, right? So particularly if I ask you any question more subtle than what will the temperature be tomorrow, right? If I ask you anything about another human being, I'm not going to know exactly anything, right? I'll get some range of possibilities. When I started, my range of possibilities was very big. And when I finished, the range of possibilities is very small. And so if you want, the entropy went down. If the possibilities were gas molecules moving around in space, then their entropy would have gone down. And so it is the decrease in entropy that gains information. And so correspondingly, you could say that the loss of information is an increase of entropy. But then what does this mean? The difference between the real difference between information and entropy is not the sign. which you just need to be careful about. The conceptual difference is that information is really always about something. So I can talk about the entropy of the gas molecules in this room, and I don't need to know what I'm planning on doing with that knowledge. But if I ask you, how much information did you gain? Then it really matters what you wanted to know. The great example of this is spelling errors. So suppose I ask you some question that can be answered by looking at the newspaper tomorrow morning. Okay? These days, I don't know whether there are questions that can be answered by looking at the newspaper in the morning, but let's imagine, I don't know, sports. Right? Who won a game? That I can learn by reading the newspaper tomorrow. But so I want to know something about what happened in the game today, but yesterday, because you guys came here, so you didn't get to see the game, so you read the newspaper. Now, there's some range of possibilities, right? About who scored and everything else. And so I can imagine there's an entropy of the text in the newspaper. Now let me add spelling errors. The entropy of the text goes up, right? Because now there are more possible texts. To first approximation, your information about what you really wanted to know doesn't change, because a few spelling errors you can read through. Interesting feature of language, very important. But eventually, it's clear that it has to go down. So the information about the thing you wanted to know went down, but if what you had wanted to know is, what are all the letters going to be in the text? Then, of course, the information went up because there are more possibilities. So when you ask questions about information, so this is one of those subtleties that I suppressed. When you really ask things about information, you have to remember, what is it that I wanted to know? So for instance, in doing image compression, you could ask, do I want to be able to reconstruct the exact image, or do I just want to be able to produce something that most people won't notice the difference? And so those are slightly different questions, right?
You have given a couple of examples where entropy is used in atomic level and information level. And you have worked heavily in neuroscience.
Yes.
So have you come across entropy, or have you utilized the concept of entropy in
Yes.
neuroscience?
So, so one thing that my colleagues and I did was, so I'm a theorist, but working together with experimentalists, what we were able to do was to actually measure, for example, how much information in bits cells in the brain are carrying about signals in the outside world. And when you ask that question, you realize that you don't know what the code is. So neurons in your brain talk to each other with sequences of pulses called action potentials or spikes. And they're about 1,000th of a second wide. And a typical cell in your brain right now is maybe generating 15 of those every second. So is the information being carried by the number of pulses that happen in a second? Or does the time at which every single pulse occurs actually mean something? That's a classical question in theories of the brain, in understanding the brain. And that's the question of what is the nature of the neural code? So what we did was we said, I don't know what the next neuron is listening for, right? But I can I can make a precise version of the question, how much information is being carried by the times of the spikes versus the number? And how does that depend on the resolution that I use in measuring the time? And what we were able to show was that in many systems, there's an enormous amount of information carried by the timing. And in fact, the information that's carried by the spike train, by the sequences of spikes, becomes close to the total entropy of all the possible arrangements of the spikes. And so in that sense, it's not quite the same as this bound from Shannon, but there's a notion of coding efficiency which is related to this. And we were actually able to show that the coding efficiency of real neurons is very, very high, which opened up a set of questions. So that's one example of where these ideas connected.
So, like you talked about the entropy and conservation of energy before in the starting. So, I have a question regarding the conservation of energy. So, at the not the atomic scale, at the subatomic scale, does the conservation of energy always work? Like we have the Casimir effect, where the particles come, like they vanish and they just pop out of existence and pop in, and so they bring energy. And like when they pop out of the existence and the fluctuations, where does their energy go? Is it a violation?
So, very good question. So, first of all, anything that you can observe will obey the conservation of energy. So we often talk about, I can take a particle and an antiparticle and send them into each other, and they vanish. But they don't vanish. Light comes out. Other stuff comes out. And if I add up all the energy, it's conserved. Now, if you look at the description of subatomic processes in quantum mechanics, we often talk as if intermediate between where the system starts, where we see it start, and where we see it end, it went through a sequence of things in between. Now, this is a very convenient way of organizing the calculation and thinking about things. Those intermediate states, which we do not observe directly, don't have to obey the conservation of energy, because we don't see them. Okay. But that's partly a problem of how we think about it. If we stick to the things that we observe, then energy is conserved. Okay? So that's the answer to part of the question. There's an important appendix to that, though, which is that if you go back to the early days of quantum mechanics in the 1920s, before the theory took its complete form, many of the great figures took seriously the possibility that maybe on a microscopic scale energy was not conserved. And there are these papers where people write about this, people that would go on to be, whom we revere as the great figures of quantum mechanics, and they're writing something that in retrospect sounds like complete nonsense. But how do you know? So the question, the question, I try to extrapolate my everyday experience down to the subatomic scale. I know that there are many things happening down there that are counterintuitive. How can I trust that conservation of energy still works? Well, that's a good question. In the end, I think that the problem is that if you don't hold to the principle of conservation of energy consistently, then you can't arrange that it only gets violated over in this small corner where you can't see it. Right? The violations will leak out and eventually get into places where you see them. Okay? So in the end, I think that's the argument. Basically, either energy is conserved or it's not. And it can't be energy is conserved except. That just doesn't work. So what is true is that as you explore the subatomic world, you find new places for the energy to go. So there are particles that we didn't know about. And in fact, one of the particles that we now know about, its existence was predicted precisely to make sure that conservation of energy held. But basically, there were a set of experiments where if you tracked all the particles you knew how to look for, energy wasn't conserved. And so people got nervous. And so it was suggested that maybe there's a particle that we're not seeing.
Gentleman at the back. He's behind the pillar. If you
Yeah. So my question is, what is the physical significance of logarithmic function coming into this picture? Like,
what's the physical significance of the logarithm?
Coming into this picture, like in this formula, what would be the physical significance? Like if I want to explain it to someone. So
yeah, why a logarithm? So maybe the easier thing to understand is if I suppose I'm trying to describe an image which is black and white. And the image has 2 pixels, very simple image. So the first pixel can be black and white, and the second pixel can be black and white. So there's black, 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 white, white, black, white, white. So there's 4 possibilities. Right? Now suppose instead of having 2 pixels, I have 4 pixels. If you do the counting, you'll discover that the number of possibilities is 4 times 4. So whenever you add pixels, you multiply possibilities. The relationship between adding and multiplying is the log.
Thanks.
The gentleman here.
Professor.
Since black holes are actually compressing things, do black holes have entropy? And isn't it against the universe law that you mentioned, second law of thermodynamics, that entropy is increasing?
So I did not get to the black hole example, in part because I don't feel like an expert there. But historically, right, there's a problem. So black holes do have entropy. And indeed, part of the issue that led to the discussion, to the notion of black holes having entropy was precisely the second law of thermodynamics. If I take an object that has a certain amount of entropy and I throw it into the black hole, it disappears from view. Where did the entropy go? So if the entropy of the universe is always increasing, the entropy of the black hole better have gone up. And it does, because it turns out that the entropy of the black hole is related to its area. And when you put more mass into the black hole, it becomes bigger. So the part of the reason for let's say, part of the path to discovery of the notion that black holes have an entropy was precisely to be sure that nothing went wrong with the second law of thermodynamics. The mystery that was left was that it's okay to have a thermodynamics, but then where was the statistical mechanics? That is to say, if I think that the entropy is not just a bookkeeping device about heat, but is also the number of ways of arranging all the microscopic degrees of freedom, all the atoms and molecules, what is the corresponding thing about black holes? And that's something that was not understood until 20-ish years ago, right? There was no candidate for understanding it. To claim that we completely understand is probably too much. But in our most modern, in our best attempt to merge quantum mechanics with general relativity, which is string theory, you can construct objects that are essentially, that would that look like classical black holes, except since this is a quantum theory, they have internal states, and you can count them. And the amazing discovery was that in these theories, if you count those internal states, you get the entropy that was the black hole entropy that was introduced by Bekenstein and Hawking as a thermodynamic object. And so even there, you get these multiple views of what entropy means that are completely consistent with each other. That is, by the way, one of the strongest results of string theory. I mean, people sometimes say that, in string theory you can't calculate anything that we can see. You could argue that this is one of the most profound examples of something that's related to something that we see.
Don't put too many hands at once. My entropy will go up. I won't be able to keep track of.
Professor, my question is related to biology and our notion of genetic engineering.
Yes.
So predictability and measurement, especially in terms of what genes get passed down and what sort of organism I'm going to generate, is one of the core principles of genetic engineering. But then entropy pays us a visit, and then we end up with results which we didn't expect. So my question is, even in a system which is quite defined as the human genome or the genetic code of any organism which has a lesser number of genes, how can I say that I still don't know all the variables and that entropy will visit me at some point and throw a curveball at me? So for example, the CRISPR-Cas9 system which we have right now and what we're trying to accomplish by eradicating certain conditions or any of those things. So my question is, where does it end?
Right. So let me back up a little bit. So indeed, entropy is the correct measure of your lack of knowledge, right? So when you gain information, your entropy is going down. It's precisely because there was a state of high entropy to begin with that you have the possibility of gaining information. If you think about trying to predict something in time, then if the thing that you're predicting, you could say that if I imagine going forward for a short time, then I'm pretty sure I know what'll happen. And so the set of things that I'm predicting has a low entropy. But then with time, that entropy will increase. And this isn't the second law of thermodynamics. This is the horizon for your ability to make forecasting or prediction. So those things are all true, and in those contexts, entropy as a measure is really the fundamental measure, and it's not a metaphor. It's really the right thing to calculate. So, similarly, when you're trying to learn something, even in modern artificial intelligence, you use entropy as a measure of your progress in learning, you're reducing uncertainty, and so on. Okay. So that's all true, and the use of entropy as a concept in thinking about predictability, very solid. The thing that you're talking about mixes a couple of different notions. So one thing is, I could genetically engineer an organism and be uncertain about exactly what's going to happen. There's another possibility, which is that I'm systematically wrong. So I'm sure it's A, and it turns out to be B. And B is very definite. Unfortunately, it's just not A. So there's no problem with entropy, right? This is just a systematic error. And I think so in our experimental friends in physics, they do a very careful, so you all learned about error bars in school and errors in measurements. So a more sophisticated version separates systematic errors and random errors. Random errors can be characterized by entropy. So I'm genuinely uncertain. Systematic errors is sort of, I might not have quite measured what I think I measured, which is very different, okay? Or my measurement might be affected by something I didn't control. So I think that it's that systematic error that is currently dominant in our ability to make predictions about, is the dangerous thing in genetic engineering. It's not, if I had a good characterization of my uncertainty, and I could describe, the entropy of possible behaviors that these genetically engineered organisms, if I could calculate in advance the entropy of behaviors that genetically engineered organisms could produce, that would be really great, right? That would imply that I understood so many things that the conversation would be in a different place. Currently, it's too much in the trial, it's in the Edisonian trial and error mode.
Sir, I want to ask you, there are research carrying out that in small amount of DNA, we can store petabytes of data. So after listening to you, I feel that that's also an application of entropy. Can you elaborate on it?
So there is a lot of work trying to use DNA as an information storage material. And of course, this is actually how life works, right? The information that you pass on to your children, you pass on the physical thing that you give them that passes on the information is a copy of your DNA. And the information, at least in principle, is very dense because if you look along the double helix of DNA in a distance which is, what is it? 3 angstroms or something like this, right? It's in a distance which is smaller than the smallest devices on the chips in your phone or in your computer, you could put an A, a T, a C, or a G, which is 4 possibilities. So you could put 2 bits in that space, at least in principle. Now, can you make all combinations and reliably read them out and everything else? That's more complicated, but at least in principle, there's the possibility of packing the information really on a molecular scale, and that's still better than the best things that you can do in silicon on chips. So there's a possibility. The thing you have to remember is that there's been 50 years and approximately $1 trillion spent on the silicon chips. So there's been an enormous amount of effort to make that technology work and to improve it. And so anytime anybody suggests an alternative, it could be that the alternative is, attractive, but getting to the point where silicon is going to be very, very hard.
We'll have 2 last questions, but before that, one more question from people who are watching it online. So there's a question from Aryaman. He's asking, what role does entropy have in the origin of life on Earth? Did the creation of life help increase the overall entropy of the universe?
So the important thing about the second law of thermodynamics is that it says that the entropy of the universe has to go up. The entropy of the small part that you happen to be watching does not have to go up. Okay? And in fact, you know about these things, right? Because you can have a chemical reaction that happens where so normally you think that in a chemical reaction, energy gets released and things get warmer, right? So you mix things together and energy, energy is released, the molecules find each other, and things get warmer. But you know there are chemical reactions when they happen, they get colder, right? And energy is sucked in. And so there's something about the sign of which way heat is flowing and everything that's completely screwed up in those examples. And so if you thought you'd done the bookkeeping right in the first example and the second law of thermodynamics holds, you might confuse yourself and think that in the other example, the second law of thermodynamics doesn't hold. And of course, it's all okay if you remember that there's a whole world surrounding this chemical reaction in which heat can flow and all the gas molecules in the room can do different things and so on. So the example that I had in mind is something that, I don't know if you've seen it, right? There are these cold packs, right? Where if you snap them, the ingredients mix and they cool off. And so these are used, for example, for people who have suffered burns, right? So that's one of those things where, you have something which actually isn't. So if I took something out of the freezer and put it on your skin to cool off your skin, I would understand what was going on, right? It's colder than you are. But here I take something which is at the same temperature you are, I mix the ingredients together, and it sucks heat out of you. Sorry, yes, it sucks heat out of you. It's sufficiently confusing that, right? And so that seems weird. But it's okay. But if you do all the accounting, it's all okay. Okay? So it's the universe whose entropy has to go down. And so that means, in particular, it's okay for part of the universe to become more ordered, as long as it gets made up somewhere else. So the emergence of life on Earth is an example of things becoming more ordered. Matter in us is much more organized than it is in the rest of the ocean out of which we came. But that's okay because the sun is shining down us all the time, right? And so all the energy of the sun is coming and heating up the whole planet, and some of that energy is being channeled into organizing matter to make us, right? And if you do the bookkeeping, the entropy of the universe is still going up. Now, when the sun stops shining, it's going to be a problem.
The gentleman over there.
Maybe I'll end on the last. The comment you made about the entropy increasing, it's a theme that's, I think, flowing through this. What's the physical basis or the genesis of that? Or is it axiomatic?
So I think that the increase of entropy historically had a slightly mystical feel to it. You know, it seems like something that is, you know, it's some rule that has to be obeyed, but where does it come from? Somehow conservation of energy doesn't bother us that much. First of all, it's a conservation law. We're used to conservation laws. In our everyday life, matter is conserved, right? If I have a certain amount of stuff, I can cut it up, I can move it into different places, I can take things, I can put them together, but the total amount of stuff always stays the same. So conservation is okay. The idea that there's something that has to keep increasing, that seems weird. And so I think that the transition from thermodynamics to statistical mechanics, where you think about the entropy as being the number of ways of arranging all the molecules, that actually helps. Because then what it says is that the reason the second law of thermodynamics is true is for the same reason that when you flip 1,000 coins, you get 500 heads. Right? There's no law that forces the last coin to come up heads or tails so that it comes out to be exactly 500. That's actually one of the gambler's fallacies, right? If you've seen 10 heads in a row, you shouldn't increase your bet on tails, right? That's not how it works. It's just that if you keep going, eventually the heads and tails will balance out. And it's that sort of statistical balancing which is what's enforcing the second law of thermodynamics. And then you might say to yourself, but wait, if I only flip 10 coins, I could actually get 10 of them all coming up heads. It's not impossible. So then the second law suddenly seems very fragile. But if I ask you how many molecules there are in this room, the number is so big that you've never seen that many coins in your life. Right? So you don't have to worry. In the limit that the number of particles that are involved in the process becomes large, all these random things become true precisely. So one of the things that was remarkable about these events in the 1800s was that, the beginning of the 1800s was the consolidation of this Newtonian view of the clockwork universe, in which everything is completely deterministic. And then we get atoms and molecules coming in, and in order to describe them, people introduce ideas of randomness and probability. Where did that come from? And in particular, how does it square with our experience of the world, which is that some things are really true? I mean, there are some things that are random, but the fact that gas expands and doesn't spontaneously contract is true. It's not true 99% of the time. And the answer is that if you actually did it with 10 molecules, it really only would be true 99% of the time. But thankfully, you never experience that. So Bertrand Russell wrote an essay called Nightmares of Eminent Persons. And what he did was he had a description of, if you end up in hell, then depending on what thing you didn't understand in life, you should be tormented by that thing. And so for the people who didn't understand all this about probability and the second law and everything else, they lived in a room where every time they open the window, all the air goes out. If they lived in a very small room, that could happen.
Last question at the back, the gentleman at the back.
Hello? Yeah. Sir, a small question. If the universe is expanding and the entropy is increasing, so the universe is expanding and the entropy is increasing. So is that some kind of a equilibrium? I mean, is there a relation between the universe expanding and the entropy of the universe increasing?
So in calculating the rate at which the universe is expanding, you have to keep track of the stuff in the universe, and you have to keep track of its entropy, but there's no problem, and it's not a trade. So you could have different scenarios. The entropy of the whole universe keeps increasing. Don't worry. The universe is expanding at the moment. There's an alternative universe which is contracting, and the entropy of the world is still increasing. I mean, you'd have to make different microscopic rules, but the entropy would still be, the second law would still be true. Because the second law isn't true because of our understanding of the way molecules interact with each other. Right? It's a statistical statement about what happens when you have lots of molecules. Good.
Okay, so with that, let's thank Bill Bialek for a wonderful talk.